All right, welcome back, everybody. Okay, so this is the end of the third week of class, and I believe we're on the 7th lecture. Okay, so I just posted homework 2 yesterday around noon. This one's a little bit more involved than the first homework. It's due a week from today. And we're going to start dealing with some real physical systems. Okay, so you're going to deal with the double spring mass system. You're also going to deal with a pendulum that's both in its stable configuration and in an inverted configuration. And I really want you to start thinking about what eigenvectors and eigenvalues physically mean for real systems in terms of the solutions of F equals MA. Okay, so just a quick overview of what we're going to do today. I'm going to tell you more about eigenvalues and eigenvectors in the context of diagonalizing ODEs. We're going to look at the geometry of eigenvalues and eigenvectors, some methods for how to solve for them in general with some examples. And then we're going to get back to solutions of the matrix system of equations x dot equals ax, thinking about phase portraits and what solutions to this ODE look like for different initial conditions. And then next week what we're going to do is we're going to start looking at, so we've been looking at these linear dynamical systems. Dynamical just means they change in time. And soon we're going to start looking at nonlinear systems where x dot equals a nonlinear function of x. Okay, so for example, a double pendulum or a satellite in the planetary gravitational field or a real elastic beam that's deflected a lot. All of these things are nonlinear. Okay, and what we're going to figure out is how to determine when we can represent those nonlinear systems with this linear equation, when this linear equation is valid, and how to analyze solutions. Okay, so we're going to go from linear systems to nonlinear systems, which opens up lots and lots of interesting physical systems. And then after that, we're going to move into the numerical analysis of these systems, because most real-world ODEs can't actually be solved in closed form. These linear ones are some of the only ones we can actually solve. Okay. Any questions about where we're going or what we've done so far or anything up to this point? Nope. Okay, good. Okay, so today we're going to talk mostly about eigenvalues and eigenvectors. Okay, so remember you can all download these notes. They're always posted, usually like a day before, but sometimes the very morning of the lecture. Okay, so I want you to recall that to diagonalize the ODE x dot equals a times x, remember x is a vector, a is a matrix, we need a coordinate transformation. And that coordinate transform looks like x is some matrix times a new variable z. Okay, so there's some linear mapping from z to x and vice versa via T inverse. So that if I wrote my dynamics in the variable z, I would have z dot equals some diagonal matrix times z. And this is much, much easier to solve. Right? We know how to solve diagonal ODEs, really simple. Okay, and so the t that we're looking for satisfies a times t equals t times some diagonal matrix. Okay? And remember that this is my eigenvalue equation. So the columns of t are eigenvectors, and the diagonal entries of d are eigenvalues. Okay, this is just review from last time. So this is a kind of matrix form of the eigenvalue eigenvector problem. Columns of t are eigenvectors. D is a diagonal matrix, and the diagonal elements are eigenvalues of A. So these are eigenvectors of A and eigenvalues of A. And so we're going to really get into the heart of what eigenvalues and eigenvectors mean and how to solve for them today. Okay, so I told you before that eigen means characteristic or latent. And the best way I've heard this German word described, so I don't speak German, but the best way I've heard this described is if you boiled a pot of the A matrix and you boiled all the water off, everything that is left, all the residual stuff, is the eigen decomposition of A. Okay, it's the characteristic or latent remainder after you've kind of done this nice factorization of the A matrix. Okay, and this matrix form is a little bit difficult to work with. So what we're going to do is use the classical form of the eigenvalue and eigenvector that most of us are familiar with, which is I have A times some vector. Sometimes I'll call it C, sometimes I'll call it X, doesn't matter, it's just a variable, equals lambda times that vector C. Okay, this is the form we're used to thinking of. So C is just a single column vector. Lambda is just a number. Okay? And so this equation is the eigenvalue equation, and it's only true for very special vectors C and for special values lambda. Okay, so if you just pick some random C vector and some random lambda out of a hat, this is almost certainly not going to be true. It's only true for very, very special vectors C and very special values lambda, the eigenvectors and eigenvalues. Okay? So let's just do a quick example and figure out kind of what the geometry of this situation looks like. Okay, so I like to think geometrically. Ordinary differential equations, physical systems are physical. They live in space, they have coordinates, and so they're fundamentally geometric. So the example I'm going to do okay, just a quick poll of the class. How many of you remember eigenvalues and eigenvectors well enough to actually compute them? How many of you probably wouldn't know all of the details if you tried to compute them by hand? It's totally fine. Took me a little while to remember. Okay, so the way I like to think about this, what we're trying to do is we're trying to find vectors ax equals lambda x. Okay, we're trying to find special vectors so that when I multiply them by a, I just scale them by some factor lambda. They get longer or shorter, or maybe they change direction. They go in the opposite direction. So first, let's just start trying some vectors. Let's see what happens when I multiply this matrix by some vectors. Okay? So I want to convince you that generically, this eigenvalue equation is not going to be true except for very, very special vectors. Okay? Okay, so let's just try x equals 1, 0. So this is the x vector. Okay, so I'm going to try a little unit vector in the x direction. I'm going to multiply it by a. Okay, so what is a times x? 3 and minus 1. Right? I take this vector, column vector, and I rotate it, and I multiply it by the first row vector, add up those numbers, multiply it by the second row vector, add up those numbers. I get 3 and minus 1. So if I draw that, I get 1, 2, 3, minus 1. Okay, so this new vector, a times x, is definitely not just lambda times x. It's in a totally different direction. There's no lambda that I can multiply x by to make it look like ax. Not an eigenvector. Okay? So now let's try x equals the y vector, 0, 1. Okay, so what does ax equal? Minus 1 and 3. Okay. So now I'm going to try this little test y vector, and I get minus 1, 1, 2, 3. That's a times y. Okay. Also, definitely not in the y direction. There's no lambda times a unit vector in y that will give me this new a times y vector, a times x vector. So neither of these are eigenvectors. That's not good. Okay, neither of those are eigenvectors. Now this is kind of an easy equation because it's symmetric. And so I might think that if I try something symmetric like x equals 1, 1, what does a times x equal? Okay. 3 minus 1 is 2. and minus 1 plus 3 is also 2. So this is good. Okay, now this vector actually is in the same direction. Okay, so my little test vector here, x, was in the 1, 1 direction. And a times x is in the 2, 2 direction. So a times x is exactly in the same direction as x, and it's exactly 2 times longer. Okay, so this is an eigenvector with lambda equals 2 as the eigenvalue. Does that make sense? Right? If I take this x, so a times x equals exactly 2 times x. So lambda equals 2. And let's try the next one. So I'm just guessing here. I haven't showed you how to actually compute these things. I could try 1 minus 1. And now what does a times x equal? 4. So 3 minus minus 1 is 4. And then minus 4. Okay, so if I start in the 1 minus 1 direction, then a times that vector is in the 1, 2, 3, 4, minus 4 direction. Okay, so a times x is in the same direction as x, and it's exactly 4 times my input x. Okay, so this is also an eigenvector with lambda equals 4. Does this make sense? Okay, this should be pretty straightforward, but what I really want to convince you of is that these eigenvalues and eigenvectors have a geometric meaning. Okay, they take my original coordinate system, x1 and x2, and they give me a new coordinate system, red direction and blue direction, so that in those directions, if I multiply by a, I stay in that direction. Okay, it's really important for differential equations, because if I have some dynamics which is stable in the red direction and unstable in the blue direction, if I start in the red direction, I'll always come in, and if I start in the blue direction, I'll always go out. Okay, so this new coordinate system is really, really useful for differential equations also. Yeah?
So does that mean you want us to think of this in terms of the vector that you're looking for, which is lambda?
Okay, so what I think about it is the eigenvectors are vectors that when you multiply them by a, they stay in the same direction. So I take my coordinate system and I find the directions where if I multiplied those directions by a, the answer would be in that same direction. Okay? And then lambda is how much a scales each of those unit vectors. And that's a really good question. So there's another point here, which is, so this is an eigenvector, right? 1, 1. But x equals 2, 2 is also an eigenvector. Right? If I take a times 2, 2, I get 6 minus 2 is 4, and minus 2 plus 6 is also 4, and this is lambda times x, right? It's 2 times x. So anything in this direction is technically an eigenvector. Okay? Usually you just pick a convention that you pick like a unit normed eigenvector. So I would probably say that the real eigenvector C1 is equal to 1 over square root of 2 in the 1, 1 direction. Okay, so this has unit length, and it's in the correct red direction. So if you type eig into MATLAB, it's going to give you a eigenvector that has unit norm, or unit length. So that's how it picks from all of the infinitely many eigenvectors. That's how it picks which one to give you. And it has some convention to give you kind of the positive one instead of the negative one also. But it doesn't always do that. So, okay, good. All right, so that's eigenvalues and eigenvectors. Now I'm going to show you how to do it in the most general case for n by n systems. Okay. So in general, we have an eigenvalue equation we're trying to solve. So we have a times x equals lambda times x. And we want to solve for lambda and x. We know what a is. Okay? Good. So I can always write a number times a vector as that number times the identity matrix times that vector. Right? Identity times x is always x. So this is the same thing. And what this allows me to do is now A and lambda identity are both matrices. They're both n by n matrices. So I can say A minus lambda n times x equals a 0 vector. Okay? This is an, ooh, that's not good. Lambda identity. So this is an n by n matrix. If I multiply it by a column vector, I get another n-dimensional column vector, and that has to equal the 0 vector. Okay? Every row of this equation has to equal 0. Good. Okay, so this is kind of the useful form of the eigenvalue equation for actually doing math. So what we have is the first case would be, like, when would this equation be satisfied? What's the simplest way to satisfy this equation? So if x was equal to 0, that would be super simple, right? X equals 0 is definitely a solution to this for every single a you can possibly name. Okay? But this is boring. This is not going to help us. Okay, so case 2 is what I heard a lot of you saying. Case 2, this could possibly be equal to 0 if a minus lambda I is singular. Okay, what does it mean for a minus lambda I to be singular? The determinant 0. So the determinant of a minus lambda I is equal to 0, which means that this is singular. Now, I'm not going to kind of rehash all of linear algebra because it would take too much time, and I'm assuming most of you have seen most of it before. But I want you to have some idea of what this condition means for determinant of a minus lambda I to be equal to 0. Okay, so what does it mean physically? What is the meaning of this determinant equaling 0? Okay, you can't invert the matrix. That's one meaning. What's another meaning? It means that some of the columns of this matrix are linearly dependent on other columns, meaning they're kind of parallel with other combinations of vectors. What is that? What's another ramification? What's a geometric interpretation of this determinant equaling 0? So I want us all to think geometrically, because I forget all the algebra I've ever learned. I was terrible at algebra. But geometry, like, we were born understanding shapes, or at least we learn them very, very quickly. Okay? So the determinant is this amazing single quantity that tells you, okay, so if I have a coordinate system, x1 and x2, and let's say I take my unit vector in x1 and x2, that defines a box with what area? 1. Okay? Now, if I map each of these vectors through my A matrix, they might do something like this. Okay? And this red parallelogram has a new area. And the area of this red parallelogram is equal to the determinant of that matrix, whatever it is. Whatever matrix I used to map these unit vectors into the red vectors, that's what my determinant is. It's the new area of this red volume. Now, you have to take this for granted. I'm not verifying this fact. I'm just telling you this is a principle of what the determinant means. In n dimensions, I have n unit vectors, and they define a cube. And what's the volume of that cube? 1. And if I take each of those unit vectors and I map them through some matrix B, that defines a new kind of parallel, crystal-looking parallelepiped. And the volume of that is exactly given by the determinant of that matrix B that I map those unit vectors through. So how could I possibly have this determinant equal 0? How could this red area actually be 0? Well, so my unit vectors can never be 0. I always have unit vectors in Rn, and they're never 0. how could I possibly have a B matrix such that this red parallelogram has 0 area? Exactly. If they map to the same vector and they collapse into a 0 width parallelogram. Okay? So what determinant 0 means, what determinant of B equals 0 means, is that I map both of those x vectors to the same direction, and so I have an empty parallelogram. Okay, that's the geometric interpretation of what the determinant equaling 0 means. And the ramification is extremely powerful. It means that I have a 2-dimensional space, and I'm collapsing it onto 1 dimension. I've lost an entire dimension in this matrix B. I've lost a degree of freedom. Okay? So I go from some high-dimensional space Rn to some lower-dimensional space Rm if my determinant is equal to 0. And what that means is that there's some direction, that gets mapped to 0. There's some vector x such that when I multiply it by this matrix, it will go to 0. Because some directions have to get mapped to 0 if I have a determinant equal to 0. So you can draw this picture. You can convince yourself that this is true. If I have a matrix B such that it has 0 area, determinant of B equals 0, then there are some directions that will get mapped to 0. That will get collapsed out when I multiply them by B. So that's what that means here, is that the only way for this equation to be true for a non-zero x is if this matrix is singular, meaning it collapses directions to 0. Okay, that's case 2. And this is called the characteristic equation, right? This is the good old characteristic equation. This is a polynomial in lambda, and the roots of that polynomial are the eigenvalues of A. So we all know how to take the determinant of a 2x2 matrix. It was in the last lecture notes. We should all know how to take the determinant of a 3x3 matrix. It's in these lecture notes. And so when you take that determinant, you get a third-order polynomial in lambda, and you can factor it, or you can plug it into MATLAB, and you can get the 3 roots. Those are your 3 eigenvalues of A. And those are the only 3 lambdas that could possibly make this matrix singular. So for those very, very special lambda values that satisfy this polynomial equation, I lose directions, and those directions that I lose are my eigenvectors x. Okay, you're going to need to go through this on your own with a 2x2 and a 3x3 matrix and convince yourself that this is true. You're going to have to try this out. You're going to have to test that this times your eigenvector really does equal 0, and plot how the unit vectors go. Convince yourself that this thing has 0 area, this parallelogram. Okay? Okay, so let's just revisit our first example. Originally, we just solved this kind of by intuition. We guessed until we found eigenvalues. So now we're going to solve it the principled way using what we just derived. Okay, so first of all, what's A minus lambda I? Equals a matrix. What is that matrix? 3 minus lambda, minus 1, minus 1. Did I mess up? Is that right? Good. Okay. What's the determinant of this matrix? Three minus lambda squared minus plus 1, minus 1. Okay, so this equals 3 minus lambda squared minus 1. I'm just going to factor this out. That's something like lambda squared minus 6 lambda plus 9 minus 1 is plus 8. Good so far? And this has to equal 0. We're looking for eigenvalues. Eigenvalues are the special lambdas that make this characteristic polynomial equal 0, the roots of this polynomial. Okay, so we can factor this thing. We get lambda minus 2. Is that right? Lambda minus 2 times lambda minus 4. Starting to look unstable, equals 0. And so my eigenvalues are I have two eigenvalues. It's a second order polynomial. So I have lambda 1 equals 2, and lambda 2 equals 4. Good. That's step 1. Step 1 is finding your eigenvalues. Finding the special values that make that a minus lambda I singular. Because the only way I'm ever going to find an eigenvector is for lambda that make this singular. Okay, questions about this first step? Nope. Okay. The first time I heard that this determinant actually had a physical meaning totally blew my mind. It's changed my life ever since. I'm really not kidding. Okay, so step 2 is, so now step 1 was find lambda, right? Step 2 is find my eigenvector, find x given lambda. Okay, so now we have lambdas that make my system singular, and I need to find which vectors x map to 0. Okay, so we start with lambda 1 equals 2. Okay, so we have a minus 2 times the identity. A minus lambda I equals what? 1 minus 1 minus 1, 1. Okay, a minus 2 identity. And this matrix times some x vector, some special eigenvector, has to equal 0. Okay, x1, x2. Okay, so a minus lambda I times x has to equal 0. That's my eigenvector equation. So what do we know about x1 and x2 from this equation? They have to be equal, right? If I plug in x1 equals x2, then I get x1 minus x1 definitely equals 0, and minus x1 plus x1 also equals 0. Okay, so this is satisfied. This is true if x1 equals x2. And so what that means is that I'm going to call it xi just so that it stands out. This is my special vector, my eigenvector xi1 corresponding to lambda 1 is equal to 1, 1. Right? x1 has to equal x2, and anything that satisfies x1 equals x2 will be an eigenvector for lambda equals 2. I mean, I did this by hand. You could also do like factorization and try to figure this out that way. Okay, good. So let's try lambda 2 equals 4. Same deal. Okay, a minus 4 lambda. Sorry, a minus lambda identity is equal to minus 1, minus 1, minus 1, minus 1. So we have minus 1, minus 1, minus 1, minus 1 times x1, x2 equals 0, 0. Okay, so how can this possibly be true for both rows? Equal and opposite. Okay. So if and only if x1 equals minus x2, which means that my second special vector, c2, is in the 1 minus 1 direction, right? x1 and x2 are in the opposite signs. Okay, so we just solved this eigenvalue problem by hand. Okay, we started with ax equals lambda xi. We multiplied this by the identity and subtracted to get a minus lambda I xi equals 0. And then we solved for lambdas where this could possibly be true for non-zero xi. And then we solved for the xi given those lambdas. Okay? That's it. You can do this for an n-by-n system. It's hard. It's very, very, very expensive. But you could do this for any system I give you now. Okay? Okay, any questions about eigenvalues and eigenvectors at all? I want this to be like multiplication used to be. This should be something that you feel deep down inside. These eigenvalues and eigenvectors for a matrix A are a new coordinate system where if I multiplied A in those coordinate directions, it would just scale those directions. Okay? So you could try this for the system. In fact, this is a homework problem. A lot of the homework problems are based around this. But we had a differential equation x double dot plus 3x dot plus 2x equals 0. And I could write this as x dot equals v, v dot equals minus 2x minus 3v, which is a system of equations d dt of xv equals a matrix 0, 1, minus 2, minus 3, xv. This is A. As practice for the homework, you should compute the eigenvalues and eigenvectors of this matrix by hand, and then use that to solve this differential equation in this form. Okay? Basically what we just did here. I tried doing this on my plane ride home from California, and I had had half a bottle of wine, and I could not do it, so I recommend being sober. The one I chose here, 3 minus 1 minus 1, 3, is a little bit easier, but not a lot. Okay. Okay, so we want to tie this back to differential equations, right? We're trying to solve systems that, have motion, F equals ma. And we started to get an idea of how we could use eigenvalues and eigenvectors in the last lecture to solve real systems that change in time. Okay? So let's see how I want to do this. Okay, in MATLAB, what is the command to compute the eigenvalues and eigenvectors of a matrix A? Eig. Okay, so I would say T D equals eig of A, and I'd probably put a semicolon so it doesn't fill my screen with garbage. Okay, and what is the fundamental relationship between T, D, and A? Right, so AT equals TD. It does not equal DT. You should try it. Like, you can't flip these two because they're matrices. Won't work. My PhD advisor pointed that out to me multiple times. So we can then say that A equals T times D times T inverse. Right? To get rid of this guy, I'm going to take the inverse on the right. And I'm going to right multiply with T inverse. This doesn't always work. I'm glossing over some details in linear algebra. I'm kind of assuming that I have either real eigenvalues or an orthogonal set of eigenvectors T. It's a little more complicated, and we'll get into that kind of in the next week or two. We'll talk about when I cannot write A like this. But for now, let's just assume that I have nice, distinct eigenvalues that are all different for a real valued matrix A, and then I'm guaranteed to have an orthogonal set of eigenvectors for T. So I can invert it. Right? If I have an orthogonal set of columns, meaning none of them are linearly dependent, its determinant is non-zero, and I can invert it. Okay, that was like all of linear algebra just now. Okay, so A equals T times D times T inverse. And so we know that A squared equals T times D squared times T inverse, right? Like, just try it. Things cancel. A cubed equals T D cubed, T inverse, and so on forever. Okay, this is a really, really, really nice, simple formula. This is fundamentally related to the fact that we pointed out earlier that if I write A in a new coordinate system T, then if I multiply A a bunch of times, those column vectors of T stay in the same direction, and they just get scaled by their eigenvalue to a power 2, then 3, then 4. Okay, so we know that our solution x dot equals AX, right? We know that this should have a solution x at times t equals a matrix e to the at times a vector x at time naught. Okay? This has to be, you can't flip the order of these because this is a matrix and this is a column vector. So you have to have x naught on the right. And now we're equipped to actually solve e to the at. We can actually write down e to the at in a convergent Taylor series using this very, very nice eigenvalue decomposition. Okay? So e to the at equals, last lecture I totally forgot to include any time. That was a mistake. So this equals an identity plus at plus 1/2 a squared t squared plus 1/3 factorial a cubed t cubed plus more stuff forever and ever and ever. Okay, a is a matrix, a squared is a matrix, a cubed is a matrix, identity is a matrix. This whole thing is a matrix, a matrix of time. Okay. Okay, but now what we can do, this is really cool, we can factor out a t on the left and a t inverse on the right. Okay, because I don't want to be computing a to the fifths and a to the tenths. Try it sometime for a real A matrix. It sucks. You can't do it. And you'll never get a nice expression. Okay, so what I'm going to do is I'm going to say this is really t times t inverse. That's the identity, right? Plus big T times d times t inverse time plus 1/2 t times d squared times t inverse time squared plus 1/3 factorial t d cubed t inverse time cubed plus so on and so forth. So all of these terms have a t on the left and a t inverse on the right. So I can say this is t times identity plus dt plus 1/2 d squared t plus 1/3 factorial d cubed t cubed plus dot 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 t inverse. Let me be a little less sloppy. This is really important. It's no time to be careless. So d cubed t cubed plus dot dot dot. All of that is right multiplied by t inverse. Right? Every term here had a t on the left and a t inverse on the right. So I just pop those on the left and the right, and I get t times this big expression only in terms of diagonal matrices, identity of the diagonal matrix, times t inverse. Okay, now this is kind of cool. All of these diagonal matrices, I know exactly what they do when I take them to a high power. Like, what's d to the 10th power? This is not as hard as it sounds. So d equals lambda 1, lambda 2, dot, 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 a bunch of zeros. What happens if I take d to the 10th power? Lambda 1 to the 10th, lambda 2 to the 10th, and then a bunch of zeros. Lambda 1 to the 10th, lambda 2 to the 10th, dot, dot, dot. Not 0, lambda n to the 10th. So all of these terms are super, super simple. And I can actually write this sum for every location in this matrix. Okay, lambda 1 plus lambda 2 squared over 2t squared plus lambda 1 cubed t cubed over 3 factorial. And what I get is, I'll just write it out long ways. Okay, so what I get is t times, now this thing looks like e to the dt, okay? And that's e to the lambda 1t, e to the lambda 2t, dot, 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 e to the lambda nt. So this is kind of the magic step that I almost skipped, so you can convince yourself that if you write out identity plus dt plus d squared t plus d cubed t, then you get a bunch of little Taylor series that add up to e to the lambda 1t, e to the lambda 2t, and so on the diagonal. Everything off diagonal is 0. Okay, so this equals, so this means e to the a t equals my big matrix of eigenvectors times e to the diagonal t times t inverse. Okay, so this is awesome. We're going to box this. This gets red with blue stars. Okay, this is one of the main results in the class. Okay, this is where linear algebra and differential equations meet, and you can solve almost any system in an incredibly simple way. E to the diagonal t is as simple as if all of my dynamics were decoupled. And the way that I can write my solution in that simplified way is by using eigenvector changes of coordinates, where t are eigenvectors of A. Okay, questions? I'm going to hammer this home one more time. This is really important. So next time on Monday, we're going to start using this expression of eigenvalues and eigenvectors to start solving 2x2 systems and analyzing their stability, their long-time behavior, their phase portraits. These are extremely useful engineering tools for very rapidly sketching what the behavior of a system will look like for long times. You can use this for feedback control if you want to stabilize a system. You can use it for design if you want some time characteristics of your system. This is going to be incredibly useful. Okay, so we have eigenvectors and eigenvalues. Yeah.
So would this be applicable to, say, a problem where you have complicated signals which you want to decompose into its constituents?
You can absolutely use this for complicated signals that you want to decompose. So the idea of using a change of coordinates, so x equals some change of coordinates z, it's useful in differential equations, right? If t are the eigenvectors of A, then that's a very useful change of coordinates for differential equations. If I have some measurement signal, like if I take my iPhone and I put it on my car and I measure the vibrations of my car, let's say I want to know what the different frequency components that it's picking up are, then I would use t, which is a discrete Fourier transform. Okay, so if I want to take the Fourier transform of something, there is a matrix T that will do it for me. The Fourier transform is a change of coordinates from my measurement data to frequency domain. Okay? There are tons of these. Wavelets is a matrix transformation. Fourier transform, matrix transformation. Eigenvectors gives me a very special matrix transform for ODEs. So thinking about the geometry, that's why I'm harping on the geometry of things, because I want us to be thinking about coordinate transformations into useful coordinate systems where things become simple. In the case of ODEs, simple means diagonal. Diagonalized dynamics. Okay, great question. Okay, good. So T is a big matrix of eigenvectors, C1, C2, Cn. D is a big diagonal matrix of eigenvalues, lambda 1, lambda 2, lambda n, zeros everywhere else. Okay, and we had x dot equals a times x. And we know that the solution, x of t equals, I think we just did it. So it's t e to the dt t inverse times x naught. Okay, so what I'm trying to show here, okay, this is just what we've done for the last 2 lectures. I have some system x dot equals ax, and I can write the solution x of t in terms of this. But what we're really doing is the following. So I take my initial condition x naught, and I multiply it by t inverse. What's t inverse x naught? Z naught, right? So z equals t inverse x. So if I take t inverse x naught, this is z naught. This is my initial condition in my eigenvector coordinate system. It's what my initial condition is if I wrote it in terms of a sum of eigenvectors. Okay, we know that in this coordinate system, z dot equals d times z. Super easy to solve. What's the solution of that? Z of t equals e to the diagonal matrix, super simple, times z naught. Okay, so we know how to solve this differential equation in the eigenvector coordinate system. But I want this in physical units. I want it in meters and x, y, and z. So what do I do finally? I have my solution in z and eigenvector coordinates. Now I map it back to x by multiplying with t. So t times zt equals x at that point of time. So that is physically what we're doing. That's what this actually means. Okay? This is a fancy expression we just derived. In fact, we derived the condition for eigenvalues and eigenvectors to find a t and a d that allows us to do this. So eigenvectors and eigenvalues are not mystical. They are specifically designed to do this. They give me a coordinate system where in that coordinate system my solution is simple, and then I can easily map back to my original measurement system. Okay, that's all I've got. We have 5 minutes if there's any questions. Okay, this has been a little bit theoretical. Next week, we're going to do examples and real A matrices. That's all. Have a great weekend.